So let me now introduce today's speaker, Chris Potts. Christopher Potts is Professor of Linguistics and by courtesy of Computer Science at Stanford University. He's the Director of the Center for the Study of Language and Information at Stanford. In his research, he develops computational models of linguistic reasoning, emotional expression, and dialogue. He's the author of the book, The Logic of Conventional Implicatures, and as well as numerous scholarly papers in linguistics and natural language processing. So thank you for joining us, Chris, and I'm happy to hand it over to you.
Thank you, Petra, and thank you everyone for turning out today. I think this is an exciting event. I also, while I have the chance, just want to thank those course alums for coming back to talk about their work. I think that's very generous. They did big and exciting things during the course, and it's great for them to be reporting out to you on what they achieved. To kick this off, I think I just want to say very boldly that we live in the most exciting moment in history for doing work in natural language understanding. It really does feel like over the past 15 years, we've seen some real qualitative changes in what we're able to do, both with technology and with kind of core scientific development. So that's a very positive picture. It really is an exciting moment. On the other hand, I think as practitioners, we can see that some of the gains aren't what they first seem, that really the big questions are still left open. And that's part of what makes this such an exciting moment, is not just that we're able to do new and exciting things, but also that the big research challenges are still ahead of us. And I think what I can do today is give you a full picture of that through the lens of what I'm going to call adversarial testing, which is a new mode of evaluating our systems and looking for ways to find problems with them and improve them. So here's kind of our outline for today. I do want to just emphasize, under the heading of a golden age for NLU, that lots of exciting things are happening. And I want that to be the overall message, that it really is an exciting moment. However, it's important that we take a peek behind the curtain and come to a measured understanding of what this progress is actually like. And that will kind of key us up to talk about adversarial testing, which is this more technical, more strategic way that we as practitioners can find fault with our systems and then look for ways to improve them. And that's kind of a nice transition into the coursework for XCS224U, because I think the tools and techniques that we introduce are really great for, combining that with adversarial testing and finding new ways to make progress. But let's kick it off on this positive note, a golden age for NLU. I've just assembled some examples that have to do with natural language understanding. Actually, I could be talking about AI in general because it really is a golden age for the entire field. First example, artificial assistants. These get a lot of the press. These are things like Siri and Google Home. The more trusting among you might have these devices in your homes listening to you at all times. They certainly pass the bar in terms of utility. They're able to help us with simple tasks around the house. I also want to just call out the fact that their speech-to-text capabilities are astounding. I think they're good in the sense that 15 years ago, the things that they achieve every day would have looked like science fiction. Now, it's by no means a solved problem. There are plenty of remaining issues with that speech-to-text. But again, it really does feel like we've made a phase change in terms of the things we can achieve there. Maybe for the NLU, a little less, as we'll see in a little bit. We don't actually talk about machine translation in the course, but I'd be remiss if I didn't bring it up because this is another major breakthrough area for language technologies. I've picked Google Translate as kind of my example here. First of all, Google Translate can take you from dozens of input languages to dozens of output languages. That alone is a kind of astounding science and technology accomplishment. But it's also remarkable how good the translations can be. Here, just as a quick example, I've put some English in on the left. I've got a French example on the right. And this is actually a kind of example from a popular data set. So we have a so-called gold translation here. And it's just striking how close the translated text is to that human gold standard. You have the usual mistakes in terms of preposition and maybe word choice and stylistics. But again, it really passes the bar in terms of helping someone who doesn't understand this input language actually figure out what was expressed. And that's just something that wasn't true 15 or 20 years ago for these MT systems. Image captioning is a really great kind of grounded language understanding task where the inputs are images and the task is to assign them accurate and interesting and descriptive captions. This is from a paper a few years ago that was a breakthrough paper, I think, on doing this kind of natural language generation. And I just want to observe that these captions are really great. A person riding a motorcycle on a dirt road, a group of young people playing a game of Frisbee. This is fluent, basically factually accurate text that is really good as a kind of caption for those systems. And again, this just wasn't something we could achieve 15 years ago. Another major technology moment for me anyway was when IBM's Watson system won Jeopardy, the online game show. This is a really integrated technology system that had to do lots of things in order to play the game of Jeopardy. But at the heart, this was a very powerful open domain question answering system. So I really do mark this as a win for NLU, that it was able to be superhuman in some sense on this show by beating these two Jeopardy champions here. And then if we zoom in on the kind of tasks that we actually focus on in the course, I think we see a similar kind of picture where the kinds of things that we can do now just feel very different from the kinds of things we could do 15 years ago. And it feels like we're on the cusp of seeing some really transformative things in the near future as well. Because it's a major unit for the course, I've picked natural language inference as the task I'm going to focus on to illustrate some of this stuff. So just briefly, the task of natural language inference, or NLI, you're given a premise and a hypothesis text. And the task is to assign one of three labels to that pair. So in this case, we would assign the label entails to the pair a turtle danced, a turtle moved. The idea is that any situation in which this premise sentence is true would also be one in which this hypothesis sentence was true. It's a kind of common sense reasoning task. Here for the second example, every reptile danced is neutral with respect to a turtle ate because they can be true or false independently of each other. And finally, some turtles walk and no turtles move would be a contradiction in this notion of common sense reasoning. So that's a fast overview of the NLI task. There are a few major benchmark data sets. The first one, the oldest one, is the Stanford Natural Language Inference corpus. Here what I've done is just map out on the y-axis the F1 score. You can think of that as a kind of notion of accuracy for the system. And in the original paper, we set a human baseline of just short of 92 on this F1 score metric. That's this red line here. Across the x-axis, I have time. And so what we're going to look at is published papers over time that have tried to achieve new things on this SNLI benchmark. So here's the picture. What you see is, first of all, basically sort of monotonic progress. I think people are learning from previous papers and figuring out new tricks that help them on the SNLI task. So you see a lot of very rapid progress. And then the striking thing is that in the middle of last year, we saw the first what you might call superhuman system for the SNLI task. So two things I want to say about that. First, again, this is not something that we could have achieved 2 decades ago. It really is remarkable that we even have systems that can enter this kind of competition, to say nothing of actually surpassing this kind of estimate of human performance. However, what we have to keep in mind, and what we'll see in a little bit, is that this does not mean that we have systems that are superhuman when it comes to the human task of common sense reasoning. All the hard aspects of that problem remain unsolved completely, and I'm going to make that very clear to you. But nonetheless, it's striking that we have systems that are even this good in this narrowly circumscribed way. Multi-NLI is a very similar data set. It's just arguably harder because the underlying data is more diverse. I have the same framework here, F1 score, and the human estimate is 92.6, so a little bit higher. And I again have time along this x-axis here. Now, it's kind of exciting that this data set, unlike the previous one, is on Kaggle, so many more people can enter and we can get their scores. So the picture overall is there's a lot more variance, a lot more people are entering and doing a lot more interesting and diverse things. But it's a similar picture in that we can see the community kind of slowly hill climbing toward what is eventually going to be superhuman performance on this task. And that's exciting to see. And NLI, just to be clear, is not the only area in which we have what you might call superhuman, but in quotes, superhuman performance. Here are a few other examples. They include speech technologies, translation, question answering, and GLUE here is a big benchmark task that captures a lot of diverse things. Again, though, you have to be really careful about how you talk about this. What we have is systems that are superhuman on these particular data sets using a very particular set of metrics. This does not mean that we have superhuman performance in any larger sense. And that's the part that I find exciting. In fact, these are unsolved problems. But nonetheless, you might look and reflect back on this technology and start to adopt the perspective that's in this book by Nick Bostrom called Superintelligence, where it kind of looks at the current state of technology and begins to wonder what life might be like when very soon, perhaps, we have systems that are vastly better than humans at all of these kind of core human abilities. And he worries about what the world and the universe might be like when we achieve those kind of breakthroughs. So have that picture in mind. I can see why people would arrive at it, given the golden age that we live in. But I do want to temper that a little bit. So let's take a peek behind the curtain at those examples. I mentioned those artificial agents before that are in your houses. You probably experience them in various ways. I think the dream is that they'll be able to do things like this. You say, any good burger joints around here? And it replies, I found a number of burger restaurants near you. And you say, what about tacos? And at that point, your device is able to recognize your intention, very flexibly think about your language and the context it's in, and kind of proactively help you solve the problem that you've implicitly defined for it. That's the dream. I'm not sure how often you all experience it. I want to balance that against this very funny sketch from the Stephen Colbert show from a number of years ago. So the premise is that Stephen has been playing with his iPhone, which has Siri on it, all day, and he has failed to write his television show. So he says, for the love of God, the cameras are on, give me something. And Siri replies, what kind of place are you looking for, camera stores or churches? As practitioners, we should pause there and kind of realize what has happened. Siri is doing some very superficial keyword matching on the utterance, not deep language understanding. And that's why it has associated cameras with camera stores and God with churches. So sort of a peek behind the curtain there. And then the interaction continues. I don't want to search for anything. I want to write the show. And Siri does what Siri often does, searching the web for search for anything. I want to write the shuffle. There's a small transcription error there, but I think the broader picture is just that Siri does not have a deep understanding of this interaction. And we're seeing on the surface here the cheap tricks that the device uses in order to try to get past those limitations. This is by no means open domain dialogue of the sort that we were hoping for. Translation, again, I think Google Translate is an astounding technological achievement, but it too shows that it doesn't have deep understanding. For this example, what I've done is just input a bunch of random vowel sequences. This is the trick I learned from the language log website. Completely random input here. It's interesting that it has inferred that this is the Hawaiian language. If you know something about Hawaiian syllable structure, you might grant that that is at least an interesting hypothesis about this input. Nonetheless, it is completely random. The really disconcerting part is that on the right here in English, we have a completely fluent sentence that by definition has nothing to do with that nonsense input. And even stranger, if I make very small changes on the left, I'll get a completely fluent but completely different sentence out on the right. And this is revealing that these systems don't know anything about their own uncertainty and certainly don't understand the inputs they're processing. I showed you before those examples from image captioning. To their credit from this excellent paper here, they didn't just show the really successful cases. Here we have a spectrum from the really good ones on the left to the really kind of embarrassing ones on the right. This middle one says a refrigerator filled with lots of food and drinks. It's actually a sign with some stickers on it. A yellow school bus parked in a lot is kind of close, but really not like what the human understanding of those scenes is. So lots of work to be done, even in the narrowly subscribed space of image captioning. I mentioned before that I think Watson was a really breakthrough technology moment for especially open domain question answering. But again, Watson did not understand what it was processing. Here's a sort of funny interaction. You have to remember that Jeopardy kind of reverses its questions and answers. So the answer came, grasshoppers eat it. And Watson's reply was kosher, which seems completely disjointed. It's not a guess that a human would make. But if you realize that Watson was primarily trained on lots of Wikipedia entries, and you look up grasshoppers on Wikipedia, you'll find very rich discussions of whether modern day grasshoppers are kosher. So there is a kind of human way in which we understand what Watson did, but this also reveals how superficial the processing techniques actually are and on how unhuman-like they actually are. So summarizing there, you might say, I showed you that perspective from the book Superintelligence before. You might, having seen behind the curtain, now balance that against the perspective from this very funny book called How to Survive a Robot Uprising. This is by Daniel Wilson, who is a practitioner, a roboticist. And this book is full of advice like, if you're being pursued by a robot, run up some stairs, or be sure to wear clothing that you know will confuse its vision system. A much more tempered perspective. So let's try to make that a little bit more precise in terms of things that we could take action on in a course like natural language understanding. That falls under the heading of adversarial testing. So just to get it into our common ground, let me quickly review what standard evaluations are like. In standard evaluations in NLU, but actually throughout the field of artificial intelligence, we work like this. You create a data set from some single process. You could scrape some data from the web or crowdsource a new data set or something like that. But the point is that it's kind of homogeneous. In the next step, you divide the data set into disjoint train and test sets, and you set the test set aside. It's under lock and key. You develop your system on the train set, never once looking at the test set, and only after all development is complete, you finally evaluate your trained system on that held out test set. And the idea is that that will provide you an estimate of your system's capacity to generalize to new cases, because after all, you held that test set under lock and key, and only at the very end did you look at how your system behaved with those entirely new examples. It sounds good, it has a lot going for it, but I want to point out how generous this is to the systems that we're developing. Because in step one, we had a single process, it's kind of too much to say that this is actually going to be an estimate of how the system will perform in the real world, because after all, the real world will throw at our system many more diverse experiences than we saw in step one and throughout this process. So adversarial testing kind of embraces that, right? Because in adversarial testing, we make a slight tweak. Start by creating a data set by whatever means you like. It could be just as before. You develop and assess your system using that data set, again, according to whatever protocols you choose. So this part could be standard. But here's the new bit. You develop a new test data set of examples that you suspect or know as a practitioner will be challenging given your system and the original data set. And then, of course, only after all system development is complete, you evaluate systems on that new test set, and you report that number as an estimate of the system's capacity to generalize. A lot of this is familiar, except for the introduction of this new and potentially quite adversarial data set in the middle here. This is kind of simulating what we saw when we looked behind the curtain, where entirely new examples that the system developers didn't anticipate were causing a lot of grief for our otherwise very good systems. Let's return to that NLI problem. Let me show you what this is like in practice. So remember, this is that premise, hypothesis, prediction task with 3 labels. In a lovely paper by Glockner et al., what they did is create a new adversarial data set that's kind of based on lexical substitutions. I actually hesitate even to call this adversarial because I think this is just kind of an interesting challenge thing that they did. So here's how it worked. You have a fixed premise. Here it's a little girl kneeling in the dirt crying. The original example had the hypothesis a little girl is very sad, and that has the entailment relation. What they did is just use WordNet, which is a structured lexical resource, to substitute here the word sad and have it become the word unhappy. Those are roughly synonymous. So what we would expect is that systems will just continue to predict the entailment relation for this new adversarial example. Everything else about the examples is the same. That's why I say this is actually kind of a friendly adversary here. What they found in practice is that systems that are otherwise very good are apt to predict something like contradiction for this second case. It's probably because they think that that negation in the word unhappy is a good signal of contradiction. So they make a mistake, and it's not a very human mistake. It's something very systematic about our understanding of a language like English that we see that these two are synonymous, assuming we know what the words mean. This example down here is similar, where you have the fixed premise, and all they've done is change wine to champagne. And that should cause a change from entailment to neutral. But in fact, since the system has a very fuzzy understanding of how wine and champagne relate to each other, it continues to predict entailment in that case. This is a picture of the data set. I think it's really cool because it's got a lot of examples, especially for contradiction and entailment. And it also has this nice breakdown by individual categories, so you can get some real insights into what it's doing. And as predicted, this is quite devastating for these systems. So I have a few models here that were very good models at the time. They have very good SNLI test accuracy. That's one of those benchmark tasks I mentioned before. And their accuracy on this new test set has plummeted by, as much as like 30 percentage points in absolute terms. So this is really devastating. Now, there is a ray of hope here. I'm not going to go into this slide in detail, of course, because there's a lot of information here. I've put it here just to say that our course has really great coverage of what are called transformer-based models. You might have heard about them like BERT, ROBERTa, Electra, XLNet. By the end of the course, you'll have a very deep understanding of all the technical details that you see here. For now, though, I would just want you to think there has been a kind of really interesting breakthrough in the last 2 years related to how people use these transformer-based models. And the way I can give you a glimpse of that, let's just highlight ROBERTa here. So what I've done on the next slide is just use some of the course code from our course and a pre-trained model that's easy to access from using Facebook code. So I read that model in and evaluate it on that full Glockner et al. Data set that I just showed you. And the result is amazing. These are the performance numbers here. The accuracy is at 0.97, and it's doing extremely well for those two categories where you have enough examples or enough support. And remember, just 2 years ago, the best system on this adversarial test wasn't even above 0.75, and now we're at 0.97 and doing well on both of these categories. That's starting to look like, yet again, some big leap forward in how well we can do. It's very exciting. Now, we can level up once more. So just quickly, so far we've been using adversaries just for test sets, but we could actually have them be part of the entire life cycle of a model. And that's what these authors have done for the adversarial NLI dataset. This is a direct response to the kind of adversarial test failings we just saw. Here's how this worked. The annotator is presented with a premise sentence and a condition, so a label they need to produce, entailment, contradiction, or neutral. The annotator writes a hypothesis, and then a state-of-the-art model comes in and makes a prediction about this new premise-hypothesis pair. If the model's prediction matches the condition, that is, if the model was correct, the annotator returns to step 2 and tries again. And you could continue that loop until the model is finally fooled, and you have a premise-hypothesis pair, which you then validate with humans. So what's happening here, by definition, is we're creating a data set that is intuitive and natural for humans, but by definition, very difficult for state-of-the-art models because they are now in the loop where people are being adversarial with them. It's a familiar picture. This is the current state of the art. So we have a few systems here that are outstanding on SNLI and multi-NLI. All these numbers in the middle here are different views of the adversarial NLI dataset, and you can just see that they are dramatically lower than those standard evaluations on the right. So another unsolved problem. We saw a glimmer of progress, but I think now this is the new thing to beat here. And in fact, we're going to hear a bit more about these kind of evaluations a bit later. So finally, just by way of wrapping up, I don't want to take too much time, but I thought I could connect this really nicely with our coursework. So here's the high-level summary. We cover these topics on the left. It's by no means an exhaustive list of topics for the field, but I think it's a good sample in the sense that it gives you a picture of a lot of different tasks, structures, models, techniques, and metrics, so that if you're good at this sample of topics, you're really empowered to take on anything that's happening in the field of NLU right now. Part of the reason I feel confident saying that is that the course is very hands-on. So we have 4 assignments, each paired with a bake-off. I'm going to tell you about the bake-offs in a second. But each one of them is meant to be a kind of simulation of a small original final project. And that culminates or leads into the final projects, which come in a sequence of things that help you incrementally build up from a literature review through in a protocol and then finally to a final paper, so that you've kind of, with the help of a teaching team mentor, slowly built to something that's an original contribution in the field. For those assignments and bake-offs, let me just give you a glimpse of what the rhythm of those is like. So each assignment culminates in a bake-off, which is an informal competition in which you enter an original model. This is like the kind of shared evaluation tasks that you see a lot throughout the field. The assignments ask you to build up some baseline systems to inform your own model design and to build that original model. And then you enter that original model into the system. We have held out test sets for you so that we really get a look at how good your systems are. And the teams that win that get some extra credit. It's also important that the teaching team assembles all of these entries and reflects insights from them back to the entire group so that we can kind of collectively learn what worked and what didn't for these problems. The rationale, of course, behind all this is that each one of these should exemplify best practices for doing NLU and help make you an expert practitioner. I want to connect back with those earlier themes, and I think we have one bake-off that does that in a really exciting way. And this is a kind of micro version of the NLI task. We do word-level entailment, where the training examples are pairs like turtle-animal, and a 1 means that they're in the entailment relation. Turtle-desk is in the 0 relation. So it's a small one-word version of that full NLI problem. The reason it connects with what I was just covering is that we try to make this a bit adversarial. So the train and test sets have disjoint vocabularies. So for example, if you do see turtle in the train set, you won't find it anywhere in these pairs that are in the test set examples. The idea is to really push systems to make sure that they are learning something that is actually generalizable information about the lexicon, as opposed to just benefiting from idiosyncrasies kind of in the patterns of the data set that happen to exist. So in that way, I think we can push ourselves to develop systems that really have robust lexical knowledge embedded in them. And these test set evaluations give you a glimpse of how much of that you've actually achieved. And just to kind of emphasize again how hands-on this all is. So this is a kind of full system for that word level entailment problem. We don't need to dive into the details of the code. I'll just say that you make essentially 3 decisions here. Under GloveVec, this is your choice of how to represent the individual words. In this case, I'm using GLOVE pre-trained representations. GLOVE is a model we cover in some detail at the start of the course. But of course, you are free to make use of any representation scheme you want for these words. You should also decide how to represent the pairs. Here I've chosen to just concatenate the 2 representations, but lots of things are possible. And then I'd say finally, the most interesting and exciting part falls under this network here. So this is a bit of PyTorch code. It's using code that we release as part of the course and that you'll make a lot of use of. The reason that's important is that that pre-built code really frees you up to think creatively about the problem at hand. And you can see that here. This is a complete working system in cell 4. Primarily what you do for this assignment and bake-off is work on this build graph method where you're essentially building the computation graph for a deep neural network model. And then everything else about the optimization process is handled by the base classes, which are already part of the course repository. And that's important because it's hidden away under base keyword args here. This model actually has lots of different settings that you can explore for different optimization choices and other things so that you can really experience in a hands-on way how best to optimize these modern deep learning models that you're building. I don't have time for it, but I did just want to mention this other bake-off. This is there are 4 in all, but this is a really different one from the previous ones. If I had more time with you, I think the other theme that I would emphasize would be the importance of grounding natural language outside of language and in actual physical scenes and stuff like that. And the way we kind of explore that in a tractable way is by doing natural language generation, where we're trying to describe color patches in context. This is another modeling direction, and it does bring in non-linguistic information in the form of these color patches. I think it's a really interesting problem. It kind of connects with interesting topics in linguistics, and it's a chance for you to explore another prominent class of models, which are these encoder-decoder models, which process sequences on the left. This is not a linguistic sequence. These are color patches. They could be images. And on the right, of course, you're producing a natural language description. But in the interest of time, I think I'll just go quickly to this wrap-up. As I said before, I really believe this. This is the most exciting moment ever in history for doing NLU. it's not like you're joining the field just at the moment when all the hard tasks have been solved. I think rather we now have a good foundation for the really exciting breakthroughs which are in the future. And I think the adversarial testing really makes that clear. This course gives you hands-on experience with a wide range of challenging NLU problems. And when you come to do your original research, you'll have a mentor from the teaching team to guide you through not only the project work, but also all those assignments and bake-offs and so forth. And the examples of success there is that some of these things have turned into really exciting and mature papers, some of them even published. And you're going to actually hear about some of that really mature and interesting work in just a moment. So the central goal, of course, of all of this is to make you the best, that is most insightful and responsible NLU researcher and practitioner, whatever you decide to do next with all of this new material. So I'll wrap up there. Thank you very much.
Thank you, Chris. This was extremely interesting. Thank you. So if you have any questions for Chris, feel free to post them in the Q&A box. We will be moving on right now to allow enough time for students to present their projects. If you are interested in learning more about the course Chris was mentioning or other courses SCPD is offering in artificial intelligence program, like machine learning or deep learning, you can check the links you will see on your platform. But now we will move on. So we will hear from two project teams that took the natural language understanding course and developed great projects that they will now briefly present. The first speaker will be Gökhan Çagrici. So Gökhan, you can go ahead.
Yes, hi everyone. So yeah, my name is Gökhan Çagrici, and my presentation is about the effect of ensembling on NLI benchmark. And our focus keyword is basically adversarial. And as you probably know, there are the leader words, and these leader words are created for some challenging problems, but most of them are using, each one of these are basically using a frozen corpus. And then there are practitioners and there are researchers who are trying to beat the best score. And this is how the life cycle goes. But you might imagine that it might not necessarily mean that you are getting the best kind of model that can generalize into new areas because of the incapability of generalizing the idea so that these models can take some shortcuts when you have a fixed kind of training and test set. So here is a paper, one of the latest papers about like incorporating this adversarial idea, and basically, as Professor Potts mentioned, it is using different rounds. So there is round one, which is basically creating this training set and test set and evaluates a state-of-the-art model, and based on the weaknesses of that model, then a new training and test set is being created, taking those weaknesses into account. And this moves on so as to challenge the model capability and increasing the generalization capability. Before we move on with the next slide, I would like to mention something. So the question is it even easy for humans, right, for an NLI task? As you see, there are very simple kind of texts, single sentence text, and very simple hypotheses based on these premises. And these judgments are being made by humans. You'll see that for example, the second example and the last example, even humans cannot agree with the correct label. So if this is the case for humans, then how are we going to approach this problem with the machines themselves? Well, as we said, we will challenge a model with progressively harder tasks. In my project, I took the data set from the paper that I mentioned, and I applied several transformer-based state-of-the-art models. So these models, actually you'll see three different models like BERT, ROBERTa, and XNet, and there are two variants One is the base one is the large one. And for the output from Y1 to Y6, you see the outputs per model. And for Y7, there is a strategy for ensembling these models and to see if ensembling is going to be a cure for us. On the right, I wanted to give a feeling about the data set. You see that this data set contains very complex and long kind of sentences, and there are a lot of named entities, a lot of relationships, references, and for the top 3 best performing models, for example, for these 2 examples, none of them could come up with the right answer. So again, we see that the task is very hard. And for the question that I mentioned, let's see if ensembling is the cure here, right? Well, these are the results for the models in isolation. We can look at just the F1 score because that is one of the scores being used by the community a lot for these problems. And even though 90+ % F1 scores have been achieved for SNLI and their variants, here we see that we couldn't even achieve a 50% kind of F1 score. And whenever we applied ensembling, yes, there is some improvement. We could barely see 51% for the F1 score, but again, it is far from like a reasonable kind of success, right? So here we see that just ensembling different models is not going to help for something that is so hard for the models in isolation. And people are using ensembling mostly for improving something that is already improved by the individual models. So then the next reasonable question to ask is, okay, why are we still far away from a very nice kind of solution? Here is a list. So yeah, model architecture can be an issue, but personally, I don't think it is one of the most critical ones. The size of the training data is as important as anything in other areas as well. So if you have a quality, if you have a high quality in terms of the training data and test data, then you have a much better chance of creating a satisfactory model. But here, even creating a training data is very expensive because, as we said, even humans are having trouble for like agreeing with the output of a hypothesis and the premise itself. So it needs a lot of effort, time, and money. But yes, it is very important. But the last one is very interesting. So if you think of a child, that child's interaction with the environment is playing a very important role, as well as like reading some text from some books and trying to analyze it. So the child is basically experimenting with the external world all the time, and then creating new hypotheses and testing it, creating another hypothesis and testing it again. So machines are lacking this ability. Maybe we are trying something that cannot be done without these machines living among us. And having said that, I would like to conclude with my experience in terms of the project and the class. Yes, it is very demanding, but something should be very demanding so as to give you better insight into that topic. And it should challenge you so that you will feel the need to learn more. And that comes actually, that is mentioned in the rewarding part. So you gain the discipline of analyzing papers, searching and comparing the results, and then trying to repeat those results or even go beyond those results. And last but not the least, the guiding part. It does not matter what kind of questions you are having, but there is a very strong kind of community from Stanford helping you. I didn't even see any question that was not answered by those expert people, including Professor Potts. And yeah, I am really happy to be here. And thanks for your time. And yeah, see you soon.
Thank you, Gökhan. Thank you for your time and presenting your project to everybody. Now we can move on to the other project that was developed by Mohan Rangarajan, Wu Pham, and Ethan Nguyen. So Mohan will now let you know a little bit more about that.
Thank you, Petra. Hi, everyone. This is Mohan. It's a privilege to be presenting here on behalf of my team, Ethan Nguyen and Wu Pham. And we're certainly looking forward to this. This quote by Mahatma Gandhi actually captures the essence of how we approach both the course and the project. We had a learning mindset, and we said we are going to learn at whatever be the cost. Right. When we actually approached the project work, we wanted to do something in question answering, obviously, and with knowledge graphs, using knowledge graphs. Right. Like many people, and like Professor Potts mentioned earlier, we were enamored with BERT, transformers, and the BERT variants, and the whole notion of contextual embedding. Right. We were curious to see how contextual embedding would improve accuracy. And so our hypothesis was really about using knowledge graph and seeing if contextual embedding would improve the accuracy. You may ask, hey, how did you come from this broad topic to a specific focused hypothesis? Right? And here we have to really talk about the structured approach that Professor Potts mentioned, doing the literary review and then the experimental protocol and then going on to the project. This really helped us narrow down to a specific focus topic on the hypothesis. So on the left-hand side, what you see here really is the broad area that we were wanting to initially look at, right? And then, one thing that we talked about is as we did the literary review, we realized that, you know what, we have to kind of narrow down our focus. And then we sought guidance from our course facilitator and, based on that direction and also looking at how much compute resources we have and the time available, we narrowed down to the natural language backend portion of this topic. And even within that, we chose the simple questions dataset. And for the knowledge graph, we chose an embedded approach to represent the knowledge graph, which was based on Freebase. I would be remiss if I don't point out here that we had complete freedom in choosing the topic, choosing our hypothesis. And so the outcome really was not a concern, right? Because the evaluation was going to be on the methodology and the rigor that we were going to have, right? And so that kind of freed us from the pressure that comes with, our hypothesis should actually improve the results, to focusing more on the methodology and the concurrence and the results there. Here is our experiment. So we had 3 fundamental tasks in the project. One was the entity learning, the other one was predicate, and the third one was entity detection. The entity learning and predicate learning models were primarily used for predicting the entity and the predicate in the simple question. And the entity detection model was useful for collecting a set of tokens that would represent entity names. For the knowledge graph, we use Freebase, and we use the embedded representation that was needed for the entity and the predicate. So the idea here really is we present the entity detection, the tokens in the entity detection to the knowledge graph, and we retrieve a set of candidate facts. And then the tail entity associated with the facts would yield our possible answer. Right? So the closest fact, since we were using embedding, the fact that was closest to the embedding representation of the entity and the predicate would result in the answer for the question. So that was kind of, in an essence, what our model was and what our experiment was about. Here's a little bit of detail on the model itself. The entity and predicate learning models were very similar. right? But the entity detection model was slightly different in the sense that, each token had to be assessed as to whether it would be a potential entity name or not. Looking at the results and analysis, we should say that we were quite pleased that there was marginal improvement in the model that we were using as compared to the baseline model. But I use the word marginal because, as you can see, it was an improvement, right? Since we were using knowledge graphs, we were also wanting to compare the results if we didn't use an embedded representation of the knowledge graph. And we were kind of, it was interesting to note that from the results, then for the individual tasks, that is entity learning and predicate learning and entity detection, right, the scores for using the knowledge graph directly without using embedding was better, right? But the interesting part is when we were actually doing the evaluation on the test set, we noticed that the embedding-based approach had better results compared to the approach without embedding. And of course, the marginal improvement in accuracy was higher compared to the baseline models that we were using. Right. So the interesting part really here is, while we were kind of pleased with the marginal improvement, we also noticed that the execution time associated with our models was much slower. Our fastest variant was twice as slow as the original model that was in the baseline. Right. And so the interesting part here is, we were then puzzled as to, okay, did contextual embedding really help in this problem or no, right? And the other part here is, we concluded then that, the training duration is slow, the improvements in accuracy were marginal. So we felt it was less compelling to use a fine-tuned BERT model for simple question answering applications in the real world. A big generalization to make, but that was our conclusion based on the simple questions dataset. And the other part to also note here is we chose the measure accuracy because it was a simple question answering solution, right? So either the answer is correct or incorrect. So what did we learn from this exercise, right? So I think it's important to understand the data set that you're using for your testing. Right. When we actually, started the project with our hypothesis, we felt that we are going to actually, have at least 90% accuracy, considering all the wonderful things BERT and the BERT variants have done actually, right? And then we realized we are kind of a bit deflated with our question. We are not performing as well, and we did a little bit more research only to realize that there is a cap of 83.4% accuracy on the model. I mean, on the, as far as using simple questions data set is concerned, right? And this is because there's a high prevalence of unanswerable questions, and some questions don't have any ground truths in the knowledge graph. Right. The other part as well is, apart from other things, we have now a deep appreciation for the level of effort required to hypothesize, research, experiment, and author a paper that conforms to ACL standards. I'd like to quote Isaac Newton here by saying, if I have seen further, it is by standing on the shoulder of giants. We really have a lot of people that we should thank for. Xia Huang and the team, whose work served as a launching pad for our work here. Salman Mohammed and the team, whose work we use as a baseline for comparing our model. The Hugging Face company, whose transformer-based models allowed us to compare different variants. Professor Potts, thank you so much. We learned a ton of new things in this course. Your active participation in the Slack channel and your enthusiasm was a welcome and pleasant surprise. Our course facilitator, Pradeep Chima, and other course facilitators that helped us, were always there to help and encourage us with our work. And lastly, Steve, it'll be remiss if we don't mention you for helping us throughout the course. Thank you so much.
Thank you, Mohan. Thank you for presenting the project. I think it's very exciting. Thank you for joining us also, Ethan and Wu, who are here with us, but not visible at this moment, but they are here. I think we can move on to the Q&A session. We got some interesting questions from the audience, so thank you everybody also for your questions. I will now ask Chris the first question. So are the adversarial examples generated by humans exclusively or by computational models such as generative adversarial network, GAN? Sorry.
Yeah, that's a great question. So you really see a full spectrum of approaches. In some cases, humans have just written new adversarial cases, as you saw with Gokhan's project with the Adversarial NLI dataset. Sometimes we can do sort of quasi-automatic stuff like with WordNet, where we just do some lexical substitutions and kind of we can assume that the meaning that we want is preserved or changed in a systematic way. But you can also have models in the loop acting as adversaries. There have been some applications of generative adversarial networks in NLU to kind of make sure these models are robust. The picture seems more mixed than you get from vision, where I know GANs have really been a powerful force for good and making models more robust. So I think there's some space for innovation there. But the general picture would be, I think we can think really flexibly and creatively about how to create those adversarial tests, and that just creating one could have its own modeling interest, in addition to that serving as a kind of new way to evaluate models. So lots of space for innovation there.
Okay, great. I hope it answered the question. The next question is about Electra-based transformer. So is Electra-based transformer more robust to adversarial examples compared to MLM-based transformer, such as BERT?
Oh, interesting. Open question. So Electra's primary motivation, I think, is to make more efficient use of its data than BERT does. We have a nice little lecture on Electra and how it works and kind of why it's successful. But in the paper, if I remember correctly, there isn't an evaluation that you would call adversarial. They mostly just post better numbers on the standard data sets and explore a really wide range of variations on the Electra model, both how it deals with data and how it's structured. But again, I love that question. It's just so interesting to ask for a model that seems to be a step forward here, not only in terms of accuracy, but also in terms of efficient use of data and compute resources. What is it doing on these very human, but ultimately very challenging adversarial data sets? Great question to address. Yeah, and it's especially fruitful if you can address that question and then maybe think about how the answer could inform an improvement to a model like Electra, because then you have that full cycle of the adversary helping us do innovative things with the models we're building.
Okay, great. The next question. It seems that there is no adversarial training in this paradigm, but only adversarial testing. Would adversarial training fit into this paradigm for NLU, or how would it work?
For sure. Yeah, so actually, Adversarial NLI, the data set that Gokhan talked about, that is large enough that you can use it for training in addition to assessment. And there are a few other data sets that are like that. Very few of them were created with the kind of full human-in-the-loop stuff that you saw with Adversarial NLI. Some of them have more automatic model-based means of creating the data sets that are large enough for training. But that's on the horizon. And in fact, one of the visionary statements that the Adversarial NLI paper makes is that we should move into a mode of kind of continually retraining and evaluating our models on data sets that were created adversarially. And that kind of ongoing process, which is a more fundamental change to how we do system development, is a kind of way to lead to even more robust systems. So my quick answer would be, we should be looking for ways to scale the adversarial testing paradigm so that we can have training sets as well.
So what is the current state of research in applications of deep RL to NLU, a part of transformers? If there is research in it, how promising is it for you, or how promising do you find it? Interesting
question. So overall, I would say the vision of reinforcement learning really resonates with me. You know, if you think about your life as an agent in the world trying to learn things and experience the environment, you don't get direct reward signals, right? You only get very indirect feedback and you have credit assignment problems. You don't know how to update your own parameters and so forth. So you have to make a lot of guesses, and it's a kind of chaotic process. But nonetheless, that's the world we live in, and we all learn effectively. So something like that set of techniques has to be brought more fully into the field. I think we're seeing really exciting stuff in the area of combining deep RL with grounded language understanding, and certainly with dialogue. And I'm sure there are other areas. So it's a great space to explore. The models tend to be hard to optimize and hard to kind of understand, but that's part of the journey toward making them really effective for the problems we look at. I'll give a quick plug. I did some stuff that I thought was really exciting that tried to use reinforcement learning together with transformer-like models to induce more modularity, so that the systems that we develop, instead of having very diffuse sort of solutions, would do things that looked more like encompassing lexical capabilities and specific functionality. And those are called recursive routing networks. Again, hard to tune, but obviously an inspiring idea. And, you know, we should just keep pushing those techniques.
Maybe one very general question. Where do you see future of NLU? What are how it will look like in the next few years?
Oh, 5 years is starting to seem like a long time. I mean, after all, my short lecture showed you that in just a 2-year span, we had what looked like a real phase change on some hard problems. So 5 years feels like an eternity. So just some predictions I could make. You know, the idea behind contextual word representations, which is primarily how transformer-based architectures are used, that's powerful and that's going to last. It really has changed things. And I think the vision there is that, like, more chances to have contextual understanding, more chances to be embedded in a context, that's going to be important. Grounded language problems are going to be more prominent, and I think that's going to lead to breakthroughs, because after all, human learners don't learn just from text. That's kind of an absurd idea. Human learners learn from the social environment, lots of inputs that they get in addition to language inputs. So to the extent that our systems can be multimodal like that, they're probably going to get better. I hope, as a personal thing, that we as a field do more to break free of the confines of always looking at English. I saw briefly in the Q&A there was a question about whether or not the field just looks at English. The big data sets tend to be in English, but I think that that's changing a little bit. For example, in the NLI problem, we now have some good multilingual data sets. And that's important because English is not representative of the world's languages. And if we look more farther afield, that might lead us to new kinds of models that would count as, again, fundamental breakthroughs. So that's going to be important. And then we should all be thinking much more. Now that our systems are more useful and more often deployed, we should be thinking more holistically, like, not just that my system did well in some narrow evaluation, but what is it actually doing out there in the world when it interacts with real examples and real users, and where the fundamental thing should be, we should be assessing, making sure that those systems are having a positive impact as opposed to causing some social process to go awry or something like that. So that's a kind of new responsibility we have that's coming from the recent successes. So a welcome challenge, but an important one.
Okay, great, thank you. We are actually at the time almost, so I would like to spend the last minute thanking you for your time to take part in this webinar. Also, both or all of them, Gökhan, also Ethan, also Mohan, also Wu, who joined us today. I think it was really interesting, exciting that they joined us and they talked about the project, so they brought it in actual live, the course materials. So thank you all for joining us. I hope you participants enjoyed it. And if you're interested more in learning more about the courses in AI professional certificate, feel free to check the links we are offering in the interface, or please feel free to contact us also directly. So thank you, everybody, and stay safe and healthy.
Thanks, Petra. Yeah, and thanks to the project teams. Those presentations were really great. I found that really inspiring.